In this lesson, we explore the primary trig ratios, sine, cosine, and tangent. In order to do this, we're going to look at a triangle. So these ratios apply to all right-angled triangles. The right angle indicated here by the little square in the corner. If we go to label this triangle, the side opposite the right angle is called the hypotenuse. It would be the longest side in the triangle. Because we're talking about this angle here, the 40 degrees, the side at the opposite end of the triangle is called the opposite side. And the other side is called the adjacent side. And it turns out that for right-angled triangles, there's an interesting relationship between the opposite, the hypotenuse, and the adjacent sides. I'm going to show you that now just by looking at a quick animation. So here we have a triangle. This angle over here is 38 degrees. And we have a list of the ratios, in this case the opposite side over the adjacent side. It just takes the opposite side, so here's the angle, the opposite side is at the opposite end of the triangle. The adjacent side would be this one right here, so maybe it's worth labeling these. Here's the opposite, here's the hypotenuse, opposite the 90 degree, and here's the adjacent side. So if we take those side lengths and divide them, you can see we get some ratios, some numbers here. The interesting thing here is that it doesn't matter if we're talking about this triangle or we're talking about another triangle with an angle of 38 degrees. You can see that the ratio of the opposite to adjacent, this one right here, stays the same. Ratio of the opposite to the hypotenuse stays the same, and the adjacent, the ratio of the adjacent to the hypotenuse always stays the same. So that's an interesting property of right-angled triangles that helps us find missing side lengths or angles. So we'll walk through that process right now. So those ratios that we just looked at have special names. The sine of the angle, theta, so I'm just going to call an angle theta. We could call it A, B, P, Q, doesn't really matter. But the sine is always equal to the opposite over the hypotenuse. The cos of an angle is always equal to the length of the adjacent side over the hypotenuse. And the tan of an angle is always equal to the opposite side divided by the length of the adjacent side. So let's see how this works in an example. So in this example, we're trying to find the length of the missing side lengths. It's the same triangle that we looked at earlier with some additional information. So here's the angle. The opposite side is over here. The hypotenuse is here. And here's the adjacent side. In this triangle, we have information about the hypotenuse, and we're trying to find the opposite. So we need to find the ratio up here, way over here, that has opposite and hypotenuse in it. So that's the sine. So we're going to go ahead and use the sine ratio. So sine theta is equal to the opposite over the hypotenuse. And then you can just fill in the values that you have. We know that the angle theta is 40 degrees. We know that the opposite side is unknown. We called it x. And the length of the hypotenuse is equal to 5. What we need to do now is to solve this equation for x. We can do that a couple of ways. I'm going to start by making the left a little simpler. Sine 40 is just a number, so you could type sine 40 on your calculator. Make sure your calculator's in degree mode. You should have a little D or a DEG somewhere near the top. And when you do the sine of 40, you get an answer like that. If you're using a phone or something, you might have to type it in backwards, so do 40 sine, and you should get that 0.6428. So the right side hasn't changed at all. And now we have an equation. It's a simple equation with one unknown x. We're trying to get x on one side of the equation all by itself. It's currently being divided by 5. We can undo that division by 5 by doing the inverse operation, and the opposite to dividing by 5 is multiplying by 5. And if we multiply by 5 on the right, we better do the same thing on the left. Plug that into the calculator, and we should get about 10.4. Ooh, something didn't go right there. And when we do that, we should get that x is equal to 3.2. So the distance here of the unknown side is 3.2 centimeters in this case. And we can kind of do a ballpark just to see approximately. We know that the hypotenuse needs to be the longest side. If we get an answer bigger than 5, and we know we've made a mistake somewhere, and it's just a matter of going back and fixing up. Let's have a look at a second example. The same sort of idea. Here's a triangle. It's a right triangle, so let's start by labeling it. Here's the 90-degree angle, so opposite that side should be the hypotenuse. The angle that we're talking about here is this 30-degree angle, so if we go across the triangle, we should get to the opposite side, leaving the other side as the adjacent side. So in this case, we have information about the adjacent side and the hypotenuse. So if you remember from earlier, the adjacent side and the hypotenuse are values that deal with the cosine ratio. So we know that the cos of theta is equal to the adjacent over the hypotenuse. And then we can plug in our values. Cos 30 is equal to the adjacent side, which is 9, over the hypotenuse, which is x. Now this question is a little different from the last one that we just did. Notice here that the variable is in the denominator. A little bit harder to solve for this one. We want the variable to be on one side of the equation all by itself, but we want it to be in the numerator. One of the easy ways to do that is just to flip this fraction upside down, look at the reciprocal, and do the same thing on the other side. You know, if we want these two equations to be equal, then we have to do the same thing. Sorry, if we want this one equation to be equal on both sides, we have to do the same thing to both sides. So if I flip one of the fractions, I have to flip the other one. Again, we know that the cos 30 is just a number. We can go to our calculators and type that into the calculator. So cos 30 is 0.8660. We still have the x over 9 on the right. And again, we can use our calculators to do 1 divided by 0.8660. And when we do that, I get 1.1547 equals x over 9. Again, we want to solve for x, so let's multiply both sides by 9. X is currently being divided by 9. Let's multiply both sides by 9 to get rid of that division. Remember, whatever we do to one side, we have to do to the other if we want it to stay balanced. On the right side now is just x. We multiply that by, we will multiply the 9 on for the left by 1.1547. And get an answer of approximately 10.4. So that indicates that the length here is about 10.4 units, whatever units that happens to be measured in. Again, the hypotenuse turned out to be longer than the other side. That's probably a good indication that we did this correctly. All right, let's move on to the last example. So the last example here is to find a missing angle. So here's a picture again. Start with the same thing. The angle we're trying to find is here. The hypotenuse is located opposite the 90-degree angle. The opposite side is at the opposite end of the triangle from the angle that we're trying to find, leaving the last side here as the adjacent side. We have information about the opposite and the adjacent sides. The ratio that uses opposite and adjacent is tan. So we know that tan of some angle is equal to the opposite over the adjacent. Opposite side is 12, the adjacent is 28, and that's equal to tan theta. So from here, doesn't look like much of an A, we can do 12 divided by 28. That works out to just a number. So the tan of theta is 0.4286. And then from here we need to get theta all by itself. So you can see that this left side has tan of theta. We want just theta. So in order to solve for theta, what we need to do is undo tan. And the way that we undo tan is with the inverse tan. So when we do that on the left, the inverse tan of tan theta, they undo each other, leaving us with theta. And then we take the inverse of tan on the right side. 0.4286. So to get to that inverse tan button on your calculator, it's probably going to be a shift tan or a second tan or something similar. And then again, your calculator will give you an answer. It's approximately 23 degrees. We're just going to round our angles to the nearest degree. So we found here that the angle inside this triangle is 23 degrees. So that's a quick introduction to the primary trig ratios.